Okay, I think it's time to start. Welcome to this afternoon. And I would like to introduce Chris Richardson. Give him a big hand.
Yeah, thank you. It's great to see a room full of people who are here to listen to my talk about how we live in somewhat of an event-centric sort of software world. So there's really two goals for the talk. One of them is just to describe how events play a very central role in our applications, both as an application integration mechanism, but also within events as well, particularly within microservice architecture. So sort of there should be a subtitle, something to do with microservices for this talk. And then I'm going to actually also talk about event sourcing, which is a particular way of building event-centric business logic, which has a bunch of benefits and fits really, really well with the microservice architecture. So those are the goals. Before I get into that, a little bit about me. So obviously, Chris Richardson. I actually live in California. Got my start in programming back in the mid to late 80s, building Lisp systems. Everything from runtimes with garbage collectors, compilers, all the way up to graphical user interfaces, IDEs, and the like. Back when machines only had 8 meg of memory. That was quite a different world. And then, eventually I ended up programming in Java, and then back in 2006, I wrote the book Pojo's in Action, which is all about how to build applications with Spring and Hibernate, which have sort of very much revolutionized enterprise Java development. And, clearly Spring continues to play a huge role within the enterprise Java world. And then back in 2007, I started tinkering around with Amazon EC2, which back then was an obscure service. Very few people had heard about it. I was running a jug, and we had invited an evangelist from Google to come speak about APIs, and he talked about the checkout APIs. And then the next month, the Amazon guy shows up, and we thought he was going to talk about APIs for buying books. But of course, it was APIs for provisioning servers, which just made my head explode, right? You could get 20 servers for 10 cents an hour, which just transformed the world, really. Anyway, I ended up building an open source project that evolved into Cloud Foundry, which was a startup for deploying Java applications on Amazon EC2. So 11 clicks of the mouse, you could upload a WAR file and have it deployed on an EC2 cluster. And then that product got acquired by SpringSource just before SpringSource was acquired by VMware. So that was back in 2009. And I spent a number of years there, sort of doing various things. Left a couple of years ago, and now I pretty much do everything related to microservices. So consulting and training around microservices, helping organizations modernize their applications. And I'm also a founder of a startup, and we're building a platform that makes it easy for application developers to write microservices, and it's got an event-driven architecture, as the name suggests, and we're looking for people to kick the tires and provide feedback, so please go check it out. A few more links. GitHub, I've got quite a few examples of event-centric microservices applications. I've got the website microservices.io, which is a pattern language that can help you apply microservices. My blog, Twitter, startup, and so on. So here's the agenda. So I'm first going to talk about events on the outside, sort of talk about how applications can exchange events as an integration mechanism. And then I'm going to talk about events on the inside and show how events play an important role in a microservice architecture, and then describe how you can build event-centric domain logic. So actually build events right into the core of your business applications, and talk a little bit about design issues and so on. All right, so let's get started. So as I said, first I'm going to talk about how applications can exchange events as part of the integration mechanism. So big question to ask is, well, what's an event, right? So if you go to a dictionary, you'll see various definitions. Party, social gathering, so on. But the one that's really relevant here is that it's something that's sort of important or notable that has happened, right? So something in a system has occurred that's worth telling the world about. And if you think about it, you know, events are sort of pretty much everywhere, right? So say when at a pharmacy, the pharmacist fulfills a prescription, I get a text message saying it's ready to pick up. So inside the pharmacy of, you know, that business enterprise, an event has happened, and I get notified as a text message. You know, my airline regularly tells me that my flight is delayed, right? That's a pretty common occurrence, especially with United. Amazon, you know, when a cookbook that I've ordered has shipped, I get notified, I'll get a shipping confirmation. And then UPS is going to tell me that, a delivery has been scheduled and it's going to arrive. So these are all notifications that I'm getting as an end user that are based on events, things that have happened inside an organization, inside some business application, actually. And then another intriguing example is Instacart, which is an online shopping application. So, you know, as a user, I place an order for groceries, and then someone in the store is walking around picking items off the shelf, putting them in their shopping cart, and then marking them as being purchased. And when they do that, I get notified in real time, and I can see which items they've actually picked off the shelves and which ones they haven't found and which ones they're still looking for, and so on. So, you know, some great examples of event sort of driven applications that kind of end up notifying me as an end user. In the general case, an event gets produced in a couple of situations. One of them is the state of a business object changes, right? A prescription is fulfilled, an order is shipped, or so on. But it also an event might get generated when a business rule is violated. So or attempted to, you know, an attempted violation. So for example, maybe my account has, you know, I try and take out too much money, and then it's good that debit is going to get rejected because my balance would go below zero, and that will trigger an event, even though the balance of my account is unchanged. So systems produce events when either of these scenarios happen. And then the question is, well, who consumes the event, right? So say in this case, an order application generates an event to say that an order has been created. That event could get consumed by by a notification service, which could send out emails or SMSs or mobile pushes to notify the end user. An event could also get consumed by another application that implements the next step of that business process. So when an order's been placed, maybe the shipping service gets notified because it's going to be responsible for actually shipping the order. Or maybe the event gets consumed by a dashboard, right, that's showing, you know, orders that have been placed today or as part of some monitoring application. So one system produces events, another application consumes those events. You know, pretty basic stuff. But it's sort of central to most business applications. So there's a few different ways within which a consumer can receive an event. So for instance, it could just poll, right? It could periodically make HTTP requests saying, give me the next event, give me the next event, and so on. A more elaborate approach, which kind of builds upon that basic HTTP polling, is the Atom publishing protocol that just adds a whole bunch of structure to the polling mechanism, and has an interesting characteristic such that you basically get a sequence of JSON or XML documents that each one contains a set of events, and they're linked together, and it's only the head of that chain that's changing, and the tail of that chain can actually be cached. It can actually use the standard HTTP caching infrastructure. So it can perform reasonably well, but as you'd imagine, it's sort of a fairly high latency, somewhat inefficient mechanism. You're just constantly opening HTTP connections to a server. Another option, of course, is to use WebSockets, right? Well, that's where a client, typically a browser, opens a long-lived connection to a server, which can then push events down to the browser, which can then update the UI. And undoubtedly, that's how Instacart updates my view of the grocery list. And it's quite common to layer other protocols on top of that. So for instance, if you're building a Spring Boot application, a Spring, or just Spring Framework application in general, you can actually use WebSockets with the Stomp protocol layered on top of it. And that gives you, that's a protocol that lets you subscribe to various destinations, and then you get message frames back. Another option is the whole webhook mechanism. So that, of course, is user-defined callbacks, right? So that's where a consumer registers registers a URL with the service saying, when any of these particular types of events get produced, execute an HTTP post to this URL. And then the service will periodically post to that URL. And that's kind of a nice sort of low latency way of just pushing events out to a consumer. And that, of course, is used quite widely throughout the web. Many web services or websites actually support some notion of webhooks, right? So Git, with which we're all from GitHub that we're pretty familiar with, lets you register a webhook. So say when someone commits a change to a repository, that GitHub will do an HTTP post to a URL, which could kick off a build or some other downstream process. Another example of webhooks is Twilio, which is telephony as a service SaaS offering, telephony and SMS. So basically, that with Twilio, your application can make and receive phone calls and send and receive text messages. So whenever you register a phone number with Twilio, you actually specify a couple of webhooks, an SMS URL that's invoked whenever a text message arrives, and a voice URL that gets invoked whenever there's an incoming phone call. So when either of those two things happen, right, someone calls that phone number, Twilio will then make an HTTP request to your application saying there's a text message, there's a phone call, and then the application can send back an HTTP response with Twilio ML, sort of markup language document that tells Twilio how to respond to the SMS or how to respond to the voice call. So if it's a voice call, it will do text-to-speech and so on. So it's a great example of sort of the power of webhooks as an integration mechanism. There are also some integration hub products. I think IFTTT is probably the most well-known, right? That's been around for quite a while. And then there's another one I discovered some sort of last year was Zapier. And what's interesting about those is that they let you tie applications together. So when an event occurs in one application, it might detect that event by either polling or by using a webhook, it will then invoke an action in some other application. So you basically set up these rules that say when this trigger occurs, which could be like you favorite a tweet or someone signs up on a website using some form collection service, it will perform some other action. And I've used that a few times to do some basic application integration, and it works quite well. Okay, so webhooks, if you think about it, is really just kind of the web version of publish-subscribe, right? It's sort of a particularly webby, HTTP-based sort of version of a more abstract notion about publish-subscribe, which occurs within just messaging systems in general. And of course, the classic definition or book about enterprise integration patterns using messaging is the book by Gregor Hope that defines a whole collection of patterns for doing message-based integration. And abstractly, it looks like this, right? Where a sender, a producer, sends a message over a channel that resides within some kind of messaging system, and then that message will get delivered to the consumer, gets delivered to a recipient. So this is sort of the behind the firewall type of message-based integration that you'd use. And there's lots of examples of message systems, right? RabbitMQ, ActiveMQ are sort of the classic ones that have been around for a while. Apache Kafka is one of those, new things that's super hot within Silicon Valley. Developed at LinkedIn, and they operate at just a humongous scale, and it's sort of the backbone of their business. And then there's another one that appears to be getting some traction, NSQ, as well. So you end up with a sort of model that looks like this, whereas behind the firewall, you've got applications that are integrated using some kind of message broker. And then outside the firewall, you have other applications. So these could be third-party ecosystem, business partner applications, or just sort of regular end-user applications that are integrated using webhooks, or WebSockets, or AtomPub, and so on. So that's sort of kind of a quick view of just events on the outside of applications. So it's really just an integration mechanism. So I want to now kind of dig into what do events look like on the inside. And interestingly, it ends up, if you dig into one of these modern applications, it kind of looks like each of the applications is really comprised of mini applications or services or microservices that are actually exchanging events in kind of the same way that applications are changing events. So it's kind of somewhat of a fractal picture in many ways. And the reason for this is, if we think about the traditional way of building applications, it's the monolithic architecture, right? I talked about this yesterday morning in my tutorial. You might have a logically modular application, lots of layers, modules, and so on, but the standard approach to deployment is to package it up as a WAR file or an EAR file and run it on some kind of application server. And on the one hand, this works really, really well for small to medium-sized applications. Monolithic applications are simple to develop and test and deploy and scale. For instance, our tools are pretty much oriented around building the application, for example. If that's like IntelliJ or Eclipse. The problem you run into is that applications have a habit of growing, right? You just have a team of people who are working away for years and years and years, and applications just get bigger and bigger and bigger. And successful applications will just live a very long time and will just keep growing. But you end up with what I call monolithic hell, where your application becomes too big, it's too unmanageable, and anything agile becomes impossible, right? Making changes becomes extremely difficult. There's just too much code for anyone to keep inside their head. And for that reason, the microservice architecture is becoming increasingly popular, right? Where you actually functionally decompose what would otherwise be a monolith, and you just have a collection of smaller standalone applications or services. So that's kind of the modern way of building large, complex applications, or at least the ideal way in many cases. But there's an interesting feature of these applications is that each service will have its own database. And the reason for that is you really want these services to be loosely coupled so that you can do as much development as possible in parallel. And as soon as two services share a database, then they're coupled. It requires a conversation between all of the people who are using that database to actually make a change to any of those tables, and that can really, really slow you down. So it's very much a best practice for each service to have its own database. So that sounds good, but as soon as you start partitioning your databases, you run into distributed data management problems. And it's also compounded by the fact that we're increasingly using NoSQL databases. So you end up with sort of this polyglot architecture where not only are there multiple databases, but you're using different types of databases as well. Elasticsearch for text search, MongoDB, Cassandra, and so on, all within the same application. So create some really, really interesting distributed data management problem. So imagine that you're dealing with you've got a business application, and it's got a customer service that's responsible for customers, and you've got an order service that's responsible for orders, right? Maybe the order service is using a NoSQL database. So if you think about transactions within a NoSQL database, they tend to be very limited. You no longer have an ACID programming model. You can at most update one row or one document within that database. And there's absolutely no notion of two-phase commits spanning multiple databases. Most NoSQL databases don't support it. And even if they did, you probably wouldn't want to use two-phase commit anyway. So it's sort of a bad idea. At the same time, you often need to have business transactions that sort of span multiple databases in order to maintain invariance, right? So the example I like to use is this customer and order example, where customers have a credit limit, and there's a business rule that says that outstanding order total cannot exceed the customer credit limit. So this means that when you're about to create a new order, you have to check that that order will not exceed the credit limit. So if orders and customers were within the same relational database, that would be a reasonably straightforward thing to do. There's some tricky issues around isolation levels and so on, but assuming you had serializable transactions, you could easily begin a transaction, check the credit limit, insert an order, commit the transaction. But if we're using microservices, then orders and customers end up in different databases, and it's sort of like, how on earth do we implement transactions that span both databases? So the approach that's preferred these days is to stay away from two-phase commit for a whole bunch of reasons, and actually use an event-driven architecture. And so the idea, of course, is that when something changes in one in one service, when it updates something, it publishes an event. Another service can subscribe to that event and update its own state, which might then trigger other events. And so you end up with these event-driven, eventually consistent workflows. And in a minute, I'll show you how you could implement a credit check using that approach. But you end up with an application architecture that looks like this, where you have a collection of services that are exchanging messages via some kind of messaging infrastructure. And it looks at, at a higher level, that's what our applications look like. So it's very fractal. So going back to customers and orders, here's how you could implement a reliable credit check mechanism. So a request comes in to create the order. It creates an order ID 4567 with a total of 343. And you can see that it's in the created state. And the order service then publishes an order created event, so it's sort of announcing to the world, I've created an order. The customer management service consumes that order, and it does the credit check. So you can see that the customer object has a credit limit attribute saying the customer's credit limit is $12,000, and then there's the credit reservations attribute that's really a map from order ID to order total. So that's the reservations of credit against the credit limit. So it can do the credit check, and it will record the fact that order 4567 has reserved $343. And then it can publish an event to say the credit has been reserved, which can get consumed by the order service, which can then update the state of the order to open, which, in other words, that this order has undergone a credit check and it's been approved. The customer service could actually publish a credit check failed event which would then get consumed by order management, which would then cancel the order and send a notification to the user. So you can sort of see how, we're using a multi-step, event-driven approach to achieve eventual consistency. And you can imagine expanding this. Maybe in addition to performing a credit check, it could also reserve inventory as well, and perhaps perform, various other functions. And the order would actually consume both the inventory reservations and the credit reservations event, and then when it receives both of them, could then say, yes, the order has been accepted or rejected, and so on. So that's the general approach, and companies like eBay have used something like this for a number of years in order to maintain consistency across multiple databases. But there's a couple of interesting problems with this approach. One is, how do you design business logic that works this way, right? It's a very different style of programming to the regular ACID programming model that we're used to. And I'm going to talk more about that later. And then the other problem you have is, how do you atomically update the database, so insert an order, and publish an event? Right? We need to actually do two things atomically, because if we inserted an order and then failed before publishing the event, our system would be in an inconsistent state. And ironically, the standard solution to interacting with both a database and a message broker would be to use two-phase commit, right? You'd sort of imagine using JMS and JDBC, and you'd enroll both of them in a distributed transaction. However, for various reasons, two-phase commit is really not an option in modern applications because of things like the CAP theorem, because of the fact that many modern pieces of infrastructure don't actually support two-phase commit. So sort of the standard approach is really just not something that we can use in our modern web scale applications. So the solution that I've sort of settled on is actually to use event sourcing. And anyone here actually using event sourcing? So, yeah. So I mean, event sourcing has been around for quite a number of years. I sort of view it as like, you got the domain-driven design community, and the event sourcing community is a little group, little subset within that. And it's always been super, super interesting to me, but more of a curiosity. But then when I started doing work with microservices, I suddenly realized that it solved some really, really interesting, challenging problems. And then looking back, it would have solved some problems that I was facing dealing with NoSQL architectures as well. So once I had this realization, I've sort of become quite a fan of using it. So the big idea around event sourcing is that, this is sort of a slight mischaracterization of it, is that rather than update the database and publish an event, which is difficult to do atomically, it just does one thing. It basically publishes an event. So that's slightly inaccurate, but at some level it's like this. And the idea, the way you end up using event sourcing is for each business entity, or in domain-driven design terms, an aggregate, you identify all of the important events or domain events for that aggregate. There's actually a technique known as event storming that people have talked about quite recently. And most of these events will correspond to state changes of that that aggregate, but they could also correspond to attempted business rule violations, like a credit check failing, for example. So you identify events, and then in your domain model, you define classes for those events. So the events become first-class citizens inside your domain model. So shopping cart, that would be item added, removed, order placed. Those would be events. For an order, it would be created, canceled, approved, rejected, shipped, and so on. So, for any entity, it's fairly straightforward to identify the events. So that in itself is sort of no big deal, right? In the sense that's just better modeling, important, but not earth-shattering. But then what event sourcing is all about is, rather than persist the current state of a business entity, so for an order, you would normally have an order table, and a given order would correspond to a row within that table. You don't actually do that. You don't store the current state of a business entity. And instead what you do is you store the sequence of events, or the state-changing events for that entity. So you could think of your entire data store of just having one table, the event table, and it just stores events for all of the different types of entities in your system. So an order would be represented by an order created event. Then there would be an order approved event. You could imagine other life cycle events, and eventually it would be an order shipped event. Maybe later on there would be the order returned event, or RMA issued, and then the order would be returned, and so on. So you just store the events that are corresponding to the various state changes of that business entity. And whenever you need the current state of an entity, you load the events and replay them to reconstruct the current state. And it tends to be very, very straightforward to do that. And of course, you might be wondering, well, if I think about a bank account that's been open for 10 years and it's got an awful lot of debits and credits, replaying all of those debits and credits to reconstruct the current balance would actually be very inefficient, and you'd be right. So the solution there is to periodically take snapshots of the current state of the entity, and then when you need its current state, you find the most recent snapshot and then load the events that have occurred since that snapshot, which is likely to be just a very few. So that's how you can make this efficient for very long-lived entities. And if you're functionally oriented, you can think of reconstructing the current state of a business entity as basically doing a functional fold over those events. So what's really interesting of this is that it kind of has yet another layer of sort of fractal ability. So before we had applications exchanging events, and then when you looked inside an application, it consisted of services exchanging events. And what event sourcing does is add another level to that, where a service consists of aggregates that exchange events. So it's sort of just at least three levels of sort of entities that are exchanging events. And in reality, it's actually the events that are coming out of the aggregates that are actually filtering all the way up and being sent to other applications. So at the aggregate level, you can think of an aggregate as this thing that takes a command and which represents a request to do something, like go create an order, cancel an order, approve an order, etc. And then it actually emits events in response to that command. And the events are both used to persist the state of that order, but also to notify other aggregates and other consumers that something notable has happened. So an order aggregate emits an order created event. A customer aggregate can subscribe to that event and and actually perform a reserve credit command, which then so there's sort of a mapping from event to command, which then emits another event which then gets consumed by the order. It turns into a command that updates the order, which emits more events. So there's kind of commands to events and events back into commands. And then, if you look at how a particular request is handled, so imagine there's a request coming in to update a particular order. First thing you have to do is go load the events for that order. You would instantiate a sort of a blank order by using its default constructor. You would then replay those events to reconstruct its current state. You'd process the command which came from the HTTP request, which would give you new events. You'd apply those events to the order to update it, and then you would save those new events in the event store. So you'd find some events and then eventually add newer events. So you're just constantly appending constantly appending events to the list of events for that entity. And you would do that with an optimistic locking check. So if there were two concurrent requests for the same order, then the first one that's saved would succeed, and then the second one would get an optimistic locking failure, and you'd then just loop round and retry in the sort of the standard thing that we should do all the time in our applications. So that's kind of how request gets handled. And then what's really interesting is other microservices can subscribe to those events, and when they get saved in the data store, the subscriber gets notified saying, here's an order created event, for example, or an order canceled event, etc. And then this consuming microservice can then update its own aggregate, which can then trigger other events. Other consumers might process those events and say, update a materialized view, which for a bunch of reasons I don't have time to go into, is very useful in the system to support queries efficiently. It might also send out notifications, so maybe it invokes Twilio to send out a text message, or SendGrid to send out an email, for example. So when you update an aggregate, an event gets saved, then the events can get consumed, which can trigger the updates of other aggregates, trigger the updates of materialized views, or turn into notifications that get sent to an end user. So there's a lot of use for these events. So the event store itself is sort of half database, half message broker. So it's a database in the sense that it has an API for inserting events for an entity, retrieving events for an entity, and then it's a message broker because it has a subscription API that lets subscribers consume events that they're interested in. There's a few different ways of implementing an event store. You know, I've talked with people who have just built their own on top of Postgres. Greg Young, who's been pioneering event sourcing, and is off in the .NET land, has his own event store. So if you go to called event store, so if you go to geteventstore.com, and then that's part of the platform that I'm working on as well. So if you look at the benefits of event sourcing, there's quite a few. So what got me excited about it is that it solves the data consistency issues in MySQL and NoSQL architectures, right? I can write these event-driven, eventually consistent business transactions fairly straightforwardly. Also, event sourcing is a very reliable way of publishing notifications whenever state changes, right? So you can feed these events into predictive analytics. You could use those events to send notifications to users, because that's an increasingly important part of what applications do. Event sourcing is also quite interesting because it eliminates sort of the age-old problem of object relational mapping. We've constantly been struggling with how do you take your complex object model and map it to a very flat, very simple relational schema. Well, the nice thing about event sourcing is you're not persisting your domain objects, you're just persisting events, which tend to have a much simpler, much more easy to serialize structure. So you tend just to be able to represent them as JSON, for example. And so you kind of generally bypass the object relational mapping problem. And then another really interesting benefit, which is really important depending on the domain, is the fact that every state change of your business object becomes an event that gets persisted. So that has two benefits. It means that you've got 100% reliable audit logging. The event can record who did what when, and because you can't change state without an event, it's guaranteed to be accurate. So that's hugely important. If you're, for instance, you're working in some domain that's heavily regulated, and it's really, really essential to know who did what when. And that's quite different from the traditional approach of doing auditing, which is where you kind of bolt it onto the application as an afterthought, and it can easily get out of sync. And then another really important benefit is because you're actually saving the entire history of every business entity, and that gives you the capability to go back in time and see what the state of it was sometime in the past. Once again, the standard approach would actually be to bolt on history. So you get this built in. So that's pretty important. And then also, you're preserving the history of everything that has happened within the system, which means that you could actually implement a feature today, pass through it all of the events that have occurred since the beginning of time in that system, and it's basically behaving as if you had implemented that feature in the past. So it's like you've almost got a time machine, which is a really intriguing idea. So there are some downsides, of course, right? It requires an application rewrite. It's a different style of coding, but then that ties in well with migrating to microservices. It's definitely a learning curve. It's a different style of writing business logic compared with ACID programming. Events, once they're written, never go away. So in theory, you could make some bad design decisions and have to live with them kind of forever. Also, because it's a messaging-based system, you have to be prepared to deal with duplicate events. That tends to be fairly straightforward. Either you have idempotent event handlers, or you just keep track of the last seen event and discard the older ones. And then another problem you can run into is sometimes querying the event store can be challenging, right? If you want to know the accounts whose balance is greater than $5,000, and all you've got is a bunch of events, that would be quite a complex SQL query to write, assuming your event store used SQL. Other event stores, like the one I'm working on, only actually gives you primary key-based lookup of your entities. So that means that you end up having to use command query responsibility segregation and maintain denormalized views of your data. So it's a complication. But for the most part, it tends to work quite well. So I want to talk really briefly in the remaining time about how domain-driven design fits into this. So I think I got my copy of the DDD book back in 2003, which seems like a lifetime ago, right? Really is a must-read book. And one of the really interesting things about DDD is that it gives you a set of building blocks, right? Entity, value, objects, services, repositories. And then there was this thing called aggregates, which at the time I just thought was kind of an interesting idea, but it really did not resonate. It turns out that domain-driven design and microservices go hand in hand really, really well. So we've got kind of a modern idea of microservices with this relatively ancient domain-driven design technique, and they work well, and aggregates end up being a central part of domain-driven of designing microservices. So what's an aggregate? So an aggregate really is a little graph of objects with a root. And it tends to correspond to business entities like customers and orders and products and so on. But there's some rules. And one of the rules is references to other aggregates can only be in terms of a primary key. So you no longer have object references between aggregates, which in traditional object-oriented design would actually be a code smell. But that has a really important benefit that I'll talk about in a minute. Also, an aggregate might actually contain copies of data from an aggregate that it's referencing. So an order line item might actually have the product name and price. And And the reason this is useful is that if you think about a standard domain model, everything tends to point to everything else, right? Which, if you want to modularize it and put different domain objects on different services, that really isn't straightforward. So the idea with this, what aggregates do, though, is basically give you a very modular domain model that's comprised of these loosely connected little clusters of objects. So an order no longer has a pointer to a customer, it just has the customer ID. An order line item no longer has a reference to a product or an object reference, it just has a product ID, which means I can just go put an order in an order service, a customer in a customer service, and a product in a product service, and there's no weird object relationships that I have to manage, which is really important. And then another idea is with aggregates is that, which I really did not get the point of at the time, is that a transaction corresponds to the update of one aggregate, which back then was like, well, I can update anything I want. I can begin a transaction, update 5 different business objects, and commit the transaction, and it just works. But if you think about the technical constraints that we're living in, of the world we're living in today, where we have NoSQL databases that have very limited transaction semantics, when we actually we've broken up our application into microservices and we can't have transactions that span multiple microservices, this notion that you have that a transaction is the update of exactly one aggregate fits in really, really well with the concept of NoSQL, or the limitations of NoSQL, and the concept of microservices, right? So we can just, if we think about the transaction scope is within a service, a service contains an aggregate, and then a request updates one aggregate. And it works really well. I mean, we do need to think about aggregate granularity, because if we do need sort of atomicity, that has to happen inside a single aggregate. And we just sort of have to think about, well, how do we break up our domain model? We could make everything in a single aggregate. Talked to someone who did that. Didn't work, but in theory you could. A customer and their orders could be an aggregate. That's not entirely unreasonable, and product would be another aggregate. But it tends to be better to have finer-grained aggregates, provided it just sort of fits within the constraints. So, kind of just threw a lot at you there. Domain events, kind of big part of this, right? So they're just sort of basically simple value objects with kind of metadata and some essential attributes that are required by the aggregates. You might actually throw other attributes in there to make it easier for the consumers. Here's an example. There's lots of boilerplate because it's Java. This would just be one line of Scala code. Commands, these are created from requests processed by aggregates. Once again, they're value objects, so they sort of look like that. A lot of boilerplate because of all the getters and stuff. And if you go look at my examples, there's various different styles from sort of a traditional Java mutable object-oriented domain object approach to the couple of different flavors of functional domain objects that are immutable. The Java one kind of looks like this, where you've got process methods that take commands and give you events. You have apply methods that take an event and do an in-place update of the aggregate. And it's really just taking a method that's sort of doing business logic or validation and state changes and splitting it into a process method that does validation, verification, gives you an event, which is then processed by a second method. So it's sort of a different style of coding, but it's really just sort of slicing up your existing business logic in a slightly different way. And in the remaining minute, kind kind of want to show you an example of an application that's built like this. So actually, this is a really boring screenshot of a Kanban board demo that I've been working on. So standard board, and you can drag tasks around. But what's interesting about it is that it's sort of multi-user collaborative, and events are used to actually update the browsers of everyone who's viewing a particular Kanban board. Architecturally, it looks like this, right? So there's an AngularJS client that uses the REST API exposed by the Kanban application. In the background, there's the event store where the event-sourced aggregates for boards and tasks live. The Kanban server uses WebSockets to push events coming out of the event store whenever a board or a task is created or updated, pushes those events over WebSockets to the browser. And then there's also a MongoDB database that's maintaining some denormalized views of the data for easier querying. And here's a simple video that sort of shows how it works. Is that, if it's running, is that actually going? Oh yeah, it's really, so I'm actually like creating a board. I've got two browsers here. And what's really cool is the bottom one is actually just getting, via WebSockets, getting events that are coming out of the event store. And then if like I create a task, you can't see it because the backlog is down here, but then when I drag stuff around, you can see that it's updating in kind of reasonable real time. So this is like from, events are going from the application running on my laptop all the way to a server that's running in AWS in Northern California and back again. And then another little benefit is that because for a given task, you have all of the event history, you can just show that to the user. You get sort of the audit logging of who changed what and when. So hopefully that kind of gives you a flavor of the style of applications you can build. So in summary, right, events are central to modern applications. You use them to integrate applications. They maintain consistency across microservices in these modern microservice applications. And then I'm a big fan of using event sourcing to build events into the core business logic of your application. So, hope that you found this useful. Here's all my contact info. Follow me on Twitter and send me email and check out microservices.io. So I hope that you found this useful, and thank you for listening.
Are there any questions? Jessica?
Could you comment on how this scale on the organizational level? How do you keep track of all of these events? Do you have any tools, or do you use Excel files or Word documents? How do you keep track of them?
Yeah, that's a really good question. I could imagine at least having a wiki for doing that. And yeah, one of the things that I've been exploring is using, for instance, JSON schema to actually define the structure of events. So I could imagine, for instance, having a Git repository that has the definitions for all of these events.
Hey.
Yeah.
How do you deal with updates? Because one of the biggest problems I see with that structure is that business evolves, and then you will have to introduce new events that, since we didn't have before, then there's a different mismatch when rebuilding the aggregate, isn't it?
Oh, yeah, that's a really great question. I mean, that whole evolution of events thing is I suppose it's quite a complex topic. I mean, so there's at least two parts to the answer. So one is often you're making backwards compatible changes to the events, right? So then the consumers of the events, which include the aggregate, just have to be smart enough to default any missing attributes, right? So that's one thing. Then if you're making backwards compatible or incompatible changes, you're basically adding events. And so either, say, an aggregate has to be capable of processing both the old and the new versions of that event, or at the sort of event store framework level, there's a mapping that happens that translates from the old event into the new event so that the aggregate only ever sees the new event. So I mean, I think in the event sourcing world, there are fairly established solutions to that problem.
I wonder if you have this lot of services producing events on an event bus and different services can subscribe to, and doesn't that lead to that it's difficult to sort of predict what will happen if you change the service that generates event because you don't really know who will consume it and what they will do about it?
Yeah. So I would sort of, if you think about what is the API of a service, right? In a traditional sort of sense, the API is really just a REST API, and we'd use Swagger for that, right? So now, basically, the API of a service is also the events that it publishes, and you just that ends up becoming an interface versioning issue at that point.
Okay, I think we have to stop there. Thank you very much. Give me a big hand, Chris.
Thank you.